Okay, morning. So I have a special mic checker today. Andre, in the chat, can you hear me? Does the mic work for you? Perfect. Okay. So let's just fix this. Okay. Better. Okay, so welcome everyone again to the lecture on embedded systems. So today we're going to talk about C programming. So we basically looked at all different aspects of embedded systems. So an embedded system is this one down here, where you have a sensor that actually senses the environment, and based on whatever it senses influences the environment again via the actuators. And it does so by having some kind of memory and some kind of processing that keeps track of all the sensors and all the environment and builds an internal model of how to modify the environment. Basically, that's the most basic thing there. And the thing about what makes a system embedded is mostly, or most commonly, the application. So that's where you can, based on an application that you have, whether it's a system that you build in a car or a smartphone app, you have different requirements to those systems, and which allow you then to make a good choice on the sensors, memory processing, and actuators that you use for this particular application. That's what makes it embedded. And we looked first into how to, that was our first part, into how we can specify those systems, how we can specify the functionality with different kind of models, Stager, Petrinets, and VHDL. And this VHDL part allowed us to specify the hardware on which our embedded system is running, if we have that. So instead of stopping our abstraction level at we have this microcontroller now, or kind of sensor, or whatever digital circuit, we can actually look into how this digital circuit is built and specified based on this VHDL, on this hardware description language, which allows us then to look at this digital circuit in more detail. Based on that, we then looked at what kind of processors you can have, what kind of memories you can have, how ADC to DAC works. This ADC to DAC, this is the part. This is the DAC part, which is basically in between our memory and processing and our actuators. So at some point, when we move from this kind of digital world with the memory and processing, and want to say, okay, this value now should have some kind of physical effect, then we do a digital to analog conversion, which basically takes our digital signal to an analog signal, which might be a moving motor or something else. Just a second now, I'll check you in a bit. The other thing is the ADC, which is exactly the other way around, where you have a sensor that has some electrical modification, an analog signal, which then converts it to a digital value. And based on these things, on this hardware, we then need to move to the software, which is basically, we looked a little bit into signal processing in this ADC and DAC chapter. And we today look at C programming. That's basically very near to the hardware. It's a programming language, which you may already know, or somebody of you has some experience with C already. 1, 2, 3, 4, 5, 6, 7. All right, that's quite a bit. So let's hope you still learn something today. Okay, so that's what we are going to do today, to look into this C programming part. Based on that one. Okay, so let me just take a quick break, and for those who have arrived late, let me just briefly scan your certificates. Okay. So the question, or one question, would be why you want to look into C, or why it's important to learn C. And I think some of you might already know C++ as well. There's a good lecture on that at the university. C is like C++ is basically an extension to C, so to say, with a lot of different extensions. And C is like a small little core, which is a small compared to C++, a small specification on the core language, which makes it sometimes a little bit easier to learn because there are less concepts. but you're also quite close to the hardware that you're actually programming. So you can do a direct memory manipulation, which you can't, for example, do in Python or which is a little bit harder to do in Python or Java. And let's call it the popularity of C is basically that the compiler is easier to port than compilers for other languages. So for example, if you want to run Java on any platform, you need to have a C compiler already running there anyway to compile the virtual machine that runs on that. So C is for most of the other language, it's the core or the foundation. So most things are implemented in C, which actually gave it its popularity. It has been around for quite some years as well. And there are still updates to the language nowadays. I think a new standard is coming out this year, which adds some new features to C. Other than that, this is from a study from Aspen Core, which basically looked at what kind of language are used for which embedded project, and what you see is that C is prevalent there still, compared to others. I mean, there are people who run Python nowadays on embedded platforms, or JavaScript, which is a possibility and has, for a particular application, also is quite nice to be able to do this. All right. Anyway, slide is a little bit overloaded, but the basic statement is that the world is running in C or on C. So if you look at most operating systems that you use on a daily basis, or the systems that you use, then most of them are actually written in C if you look a little bit closer. So if you use iOS, then the kernel is running in C. Linux, of course, is running on C. Windows is running on C, or your mobile operating systems. And most programming languages, or most higher level programming languages, have an easy interface, have at least an easy interface to a C program, or they are based or implemented in C. So said, for example, the Java virtual machine, that's implemented, for example, in C, as most of the operating systems for your devices. If you don't believe me, there are a few more links that you can read up on this, which gives a little bit more of an idea of where C is used. So that's why we are looking into C. That's why we're looking into C. You have a few book recommendations where this chapter is based on, and I think if you want to go into C and you don't have that much time to actually learn it, then you can look for the book by the original authors of the C programming language. That's Cunningham and Ritchie. They have written a book. The C programming language is about 60 to 80 pages, which gives you a really good understanding of C. And this chapter that I'm looking at is based on this book. I probably don't do. They probably do a better job than I do in introducing you to C, but it's again interactive. So I hope there's something to get from it. Other things for good programming tricks when you implement something in C, just a second, is to look into this book, the Beautiful Code book, which is also quite well written and gives you some idea of nice programming tricks. Just a second. Right up. All right, perfect. All right, the next one is the secret of reverse engineering. That's actually quite interesting because it gives you a really well understanding of the hardware that you're actually looking at. That's something C tries to abstract a little bit away from, so you're still quite near to the hardware. It's more or less almost assembly language in a way. But the secret of reverse engineering actually gives you a good idea of the hardware or particular things that you can learn about the hardware that you're running your programs on, which is also quite good. All right, but these three books and, of course, the reference to C will give you a good overview of what is there to come if you need to look into something. All right, so as I said, C is quite near to the machine that you're actually programming. So the first thing to understand before we can go into C and the syntax and how you actually structure your programs in C and what kind of features you have is to look into machine models, and that's how a machine actually executes executes instructions. There are different models of how to do this. The most basic one and the most, no, not the most basic one, but the one that you most often use and that you can use as a, so to say, model of how a machine works is the von Neumann architecture. And the von Neumann architecture means that you do a serial execution of instruction that modify memory. That's kind of the basic thing that you have. And what we are looking at is into a special kind of architecture of this one, which is called a register machine. That means that you have a small amount of memory that's close to your CPU, to your processing core, that you can modify, and you can then transport those register values that you calculate into the main memory again. And that's what's happening from the memory manipulation side. And the other thing is that you execute an instruction, then you execute the next instruction, and you execute the next instruction, then you execute the next instruction. And each of these instructions modify the memory somehow. You either make a modification on the register value, or you take a register value, store it into main memory, or load some kind of memory value from the main memory into a register value. That's all there is to this one. And you have the like standard registers, which you can sometimes call R0, R1 to R16, R32. Sometimes they are prefixed with an A or an X. That depends on the whatever machine you're using, but there is usually this register file that you modify. Then there's the main memory. As I said, it's just a block of memory addresses which stores values, so single bits, which is then connected to your CPU. There's one special register that's that you have for all of those von Neumann machines, and that's called a PC. And that's short for the program counter. That actually keeps track of the next instruction to be loaded or the current instruction that's executed. So what your CPU does in this von Neumann model, or what your machine generally does, is to, and that's what you need to keep in mind, is that you execute an instruction A, some kind of instruction that has maybe one operand or two operands. Then you, once this instruction is finished, you execute the next one, which might be one operand, which is also where one operand is a constant value, the other one is a register file. Then you execute the next instruction where you maybe check whether a value in a register is equal to something, and based on that you either continue with the next instruction or you reset the program counter to continue executing somewhere else, right? So for example, you might say, okay, I want to, if those things are equal, I want to program a loop and I want to go back to the first instruction and continue there, or once it's not equal anymore, I want to execute the next instruction and continue here. So this is called then a branching, or this is called a branching operation. Now, of course, if you have something like this, if you want to do branching or jump around in your program and execute somewhere else, you need some kind of addressing mode, and this is very simple. These instructions are nowadays, and since quite a few years, stored in memory itself. That's another thing for the von Neumann machine. These instructions now, let's say we basically enumerate all the memory addresses that we have, and we store the instructions there. Then we have this memory address where we start our execution when we power up or when we reset the CPU. And then we start from there to execute our single set of instructions. And now we can basically enumerate those instructions and so forth, and they are stored in memory. And for the von Neumann model, there's no difference between the memory that we modify with our program and the memory where our program is stored. There's no distinction between this. All the instructions are stored in the normal memory. We can basically modify our program can start to modify itself, so to say. We can overwrite the instructions that we write. And that's the thing for the von Neumann model. So there's one single part of the memory, the program is stored there, and it just serially starts somewhere in memory, usually address 0 or the so-called reset vector, starts to execute different instructions. This might be branch instructions, jump instructions, arithmetic instructions like multiplication, for example, to calculate things. And there are some kind of Boolean arithmetic operations, and there are comparison functions, like checking for equality or checking whether some value is larger or smaller than another value. Those instructions that you have here, or the set of instructions that you can execute for your CPU, is called the instruction set. And there are different things. So if we talk about an ARM machine or ARM CPU, then basically it refers to this instruction set, the kind of instructions that you can execute on this machine. Another one would be x86 or the RISC-V instruction set, the MIPS instruction set, and so forth. These are different instructions that you can execute here on your CPU. But the basic idea behind this is always the same. It's mostly this von Neumann idea, where you have a CPU that takes one instruction, executes it, then takes the next instruction, executes it, takes the next instruction, executes it. In between, you have, and in between, you only have this defined state where you say, okay, if I stop the program at any of those instructions at any instance, then the memory is exactly as if I would have executed this instruction to this end. So if you stop the program here, for example, stopping the program means you halt the clock on the CPU, so it basically stops executing the next instruction, doesn't get this one, and you inspect the memory, you will always get the same defined state if you stop this program there. So this might be a little bit confusing why I say this, if you don't know how a CPU actually executes an instruction. So this one instruction after the next instruction is actually a simplified model of how a CPU works internally. It's a lot more complicated, and if you want to squeeze out more performance, you do something like, for example, pipelining, or you're allowed to reorder those instructions, as long as you make sure that if you stop the program at any instance, this basic assumption that there's one instruction executed after the next, and you stop it at this instant, the memory always looks the same. So you always pretend, from our point of view, we always pretend that if we look at a CPU and how it executes just one instruction after the next instruction after the next instruction. In the real world, as I said, there could be reordering, pipelining, and if you want to go into more detail how this works, then there's the computer architecture lecture that actually teaches how those CPU works below this level. But for us, and for C programming and for anything else, we can assume, or we can take this von Neumann assumption that one instruction after the next. Right. So this is the von Neumann and those instruction sets. Now, one thing that we looked at, or that I asked you beforehand, is what's the difference between an 8, 16, and 32-bit, 64-bit, 180-bit CPU. And one difference is this connection here, and the bit width of this connection between the CPU and the memory. So if we talk about a 32-bit, it usually is a 32-bit or 32-bit wide memory accesses that you can execute in one clock cycle via this memory bus. The other thing is that your registers here, if we talk about a 32-bit CPU, are exactly 32 bits wide, which also means all your instructions work on 32-bit operands, or can work on 32-bit operands, and this instruction here, together with its operands, has exactly 32 bits to be encoded. That's also the difference between the ARM x86 RISC-V the CPU is how those 32 bits actually designate an instruction. So this is a particular bit pattern that you have, for example, if you want to encode a branch instruction, is how you encode, first of all, that it is a branch instruction. So you have a particular bit pattern. This might be, I don't know now for the RISC-V CPU, but we can look at this in a second, in a later slides, is that you have a particular bit pattern that encodes, okay, this is a branch instruction for the RISC-V CPU, and then you can encode, for example, that you want to have register file 1 as 5 bits on this one. And that's the difference between those instruction set architectures, how those are encoded. Right, but as I said, for us, we take this von Neumann instruction. We have a memory that is modified by a set of instructions, and our CPU does nothing more but execute instruction, the first instruction, next instruction, next instruction, next instruction. And those next instructions is coming from the program counter register file. So this program counter, this always tells the CPU where to get, at which address the next instruction is coming from. So this means in the default case, it will always be incremented by 4 or 8 bytes, depending on whether you have a 32-bit or 64-bit CPU, or it's modified by a jump instruction, which basically just resets the PC to somewhere else where the execution should continue, or by branch instruction, which is the same, but depending on a certain condition on your memory. Right. This is what the basic model is. There's one more quite common one, which is called the Harvard architecture. The basic principle is the same. We execute instruction after instructions. The only difference now is, and this is something that you find commonly in an embedded system, not so much on a larger CPU, because there's a different mechanism for achieving the same. But here in the Harvard architecture, you have a separation between the data memory and the program memory. Now, my question is, do you have a guess why you want to divide those two memories? Why you want to have a separate program memory where you store your program, and a data memory where you basically have your working memory for your program. You store all the results. Calculate. There are several reasons for that. Any idea why? Okay, there are a few answers in the chat. One is security. Correct. Get into that in a second. Why? Security, speed and performance. Also get into that why. Yeah, security, there's also the reason for that, given you could break your program by altering it, that's true. And for the performance, the answer is while doing an instruction, another instruction could be loaded. Absolutely correct. These are the two main things of why you want to do this. It's one, security or safety, not necessarily security, that's a different term, but more or less safety. And the idea behind this is that if you have a misbehaving program, or if you have a bug in your program, then it could happen if you don't have any memory protection. And this is a kind of memory protection, is that you can rewrite parts of your program and basically break it in even worse way than your bug originally assumed. So by dividing this, you can actually say, okay, if my program wants to modify memory that's actually program memory, so where my program is stored, I can do the CPU can throw an exception and actually tell the programmer about it. So that's one part. So one thing is the memory protection. It's a very simple one, or very simple way of doing memory protection. That's a good one. The other one is speed. And there's also the one person also said SRAM versus DRAM, which is true. So speed is one thing about this. So if you depending on how you do this architecture, so in this way I draw it on one single bus. So there you don't get a speed gain, because you can't transfer multiple things in one clock cycle via the same bus. What you could do, however, if you have separate program and data memory, is that you have one bus for the data memory, one bus for the program memory, and now you can basically load an instruction from the program memory bus and load or modify data on the data memory bus at the same time. So you don't have this speed or this congestion on the bus, on a memory bus, which is, by the way, sometimes also referred to the von Neumann bottleneck. It's exactly this bus problem that you need to do a lot more memory access than what your bus can handle at one point. Right. So speed is definitely one thing by dividing this bus memory. The other thing is so divided, separate bus access. down. The other thing is on this, not necessarily speed, but if you have those two different programs and data memories, is that you can have different types of memory. The idea why you want to have different types of memory for the data and program memory? Any guess? Think about different memory types. Okay, one answer is cost. Yeah, in a way you could use slower memory for one. So that's coming from the chat, but there's a different reason for that.
Well, I guess because for memory we are going to write a lot on it, raise it and a lot in it because we are burning the code on it. While the data memory we can store the data we want. So this would be a flash memory and this would be
Yeah, right. So your guess is that the data memory is written and read a lot more often than the program memory?
more often than
so the data memory is the one that you modify from your program. The program memory is where you store your program. Yeah, but usually, I get, but usually it's the other way around. So you don't modify your program memory that often because basically it's just static and you execute it most of the time. So once you've written your program and once it's fixed, you don't modify it anymore. While the data memory is modified a lot more. But it's but you're right. The other thing that you said is that you want to have this one in flash memory and this one in some kind of RAM. And that's a good thing because this one here should be non-volatile. Because you don't want, whenever you power cycle your CPU or whenever your architecture changes, you don't want to, well, basically have to get your program from somewhere. So you want to store it in some kind of flash memory that basically lives through power cycling the whole system, right? So that you can keep your program stored for longer than a few seconds or while your battery is running. And some of those architectures actually do this directly. So you have this program memory, which directly accesses the flash memory to retrieve the programs instead of doing instead of storing this somewhere else. So it's an architecture where you have where when you directly have a connection to the program memory, it's usually some kind of non-volatile memory that you have to store your program in. The other way, if you have a von Neumann machine where you only have a single memory, then this is of course a on oversimplification. So if this is RAM, then you usually have also some kind of connection to a non-volatile memory, which could be some kind of flash memory. And when you reset the CPU or when you boot the CPU, you usually then copy your program from this flash memory into the RAM memory before you can execute something, so that you can also keep the program there between resets. Okay, so speed is one thing, and this non-volatile thing if you have different types of memory that you want to support for the Harvard architecture. All right, these are the two things that you will have. And as I said, this is the other thing again. So memory protection and security and safety. So if you have a little bit more advanced CPU, so not the one, if you don't have like a super simple embedded CPU that allows you to save a lot of power, then you sometimes have something called an MMU, a memory mapping unit, or sometimes these are also called MPUs, a memory protection unit. These memory protection units, this is something that you can learn about in the operating systems lecture. This is basically an indirection between the memory access. So instead of accessing memory directly from your program, you basically have another table in between that gives you a little bit more control of which program or which part of your program can access which kind of memory. And this allows you then to run multiple programs at the same time on your CPU, but you can then make sure that those programs don't influence each other that much. That's the idea behind this, but this requires then additional hardware, some kind of table in between memory accesses. Right, but as I said, more details on that in the operating systems section. So again, no matter how your memory architecture looks in your embedded systems, the thing is always the same. You have this execution cycle. So at some point, so you have some kind of memory somewhere which stores an instruction 1, then your next instruction, and so forth. And here you have an instructions. You have different so-called labels in between where you can jump around, and some of those instructions jump back or forward into this execution cycle. What your CPU now does is what you see here on the left-hand side. So you basically go to start your CPU or reset your CPU, which means you basically have a designated address in your CPU where from which you start to execute instructions. This means you set a PC to this well-defined reset vector. This might be 0. So here the effect of this one is to set the program counter register to 0. And then what happens in this execution cycle is that we fetch the PC. This means we get the first instruction. We load this one. We then put this into the decoder of our CPU, which basically means all the lines inside of our CPU are set to the correct values, whether this is an AU instruction, a branch instruction, and so forth, which will then execute. And the result of this execution of this instruction will then be stored inside of the memory. And all this happens in, this is all one cycle, or this all happens for our model, all happens in one execution cycle or one clock cycle. And then after this result has been stored back into main memory, there's one thing that is a little bit different than what I've told you before, and that's we check whether there was an interrupt. And those interrupts, these might be connections to your CPU from the outside. So for a microcontroller, you usually have some kind of block with a few lines running in and out of this CPU. And what you can have here is special designated interrupt lines, where there's a comparator behind this, which is executed to, which is compared, for example, to VCC. And what you can then check for is whether this line is high or low. And if it is, you stop your normal execution cycle. So instead of, if there's no IRQ, we just fetch the next PC. So whether this was a branch, we just execute somewhere else on our program. But if there was an interrupt, so if, for example, one of those designated interrupt lines went high, then what we do is we set our PC to a special IRQ vector, or basically some designated address where we say, okay, this is where we store our interrupt program. And what it does is then to stop the current execution wherever we are. So if we have a list of instructions, we basically just check in between all those instructions, or then there was an interrupt, so now I need to check. Now I need to go somewhere else. The PC is reset, executes a different program, which hopefully stores the complete state of our CPU, briefly executes whatever should be happening there. For example, this could be, okay, now I need to set a flag somewhere in the memory so my main program can check later on whether there was an interrupt happening. Executes this, restores the CPU state, and then, once all this stuff is done, resets the PC to what it should have been if there was no interrupt. So we just continue executing as normal. And that's basically it, what should happen. In this execution cycle, this is what you can assume from a normal CPU. So no matter how your CPU executes those instructions, whether they are optimized, reordered, or pipeline, or something else, this assumption is true for all of them. You start at some point, you execute whatever the PC says, whatever your program counter says. If there is an interrupt between two instructions, then you basically continue somewhere else, execute this briefly, and then return back from this interrupt handler for this exception to the normal operation of executions. That's all there is happening for whatever CPU you are using. Okay. Any idea to make sure that that this interrupt is not going to be executed in between your instructions if you don't want it to. So-called atomic instructions of critical sections in your program. Could, for example, have the thing that you want to have several instructions that need to be executed in order for your program to function correctly. So you want to make sure that it's not preempted by anything happening from the outside. Any idea how to do that? Yeah. Exactly, yeah. That's the trick to do. So you can usually mask this thing here, or an interrupt mask. The idea is then to completely disable these interrupts and re-enable it after you've left the critical section or the atomic section that you want to execute. Correct. All right. Another one from the chat is locks. And this is actually similar to that. There you have an atomic critical section to implement those locks. And this is usually done, or mostly done, by masking interrupts or by completely disabling them. Okay. So as I said, the difference between those instructions at RISC-V, ARMX86, or anything is basically the encoding of those instructions. Here's an example of the ARM instruction set for 32 bits. What you see here is whatever instruction is going to be executed. Here you see this encoding for those instructions. So this part here, or parts of this one, I think here it is like this. These actually encode. No, this one with the opcode. These actually encode what kind of instruction should be executed. Everything else behind it is a configuration or operands to those instructions that you use. And this is the main difference. If you have a RISC-V CPU, they look different and so forth. But what you can see is that usually you have something like branch instructions, you have arithmetic instructions, and a few more different ones that you can use. This is what the CPU executes. Now, if you look at memory, and this is one part of our machine model. So this execution, we execute one instruction. After one instruction, if there's an interrupt, we execute another one. And we modify the memory. And those memory things that we have are addressed with a memory address. This is this one. At the start, some hexadecimal value that you can have. And we divide this memory that we can execute into so-called sections that are then mapped during the compilation process for a C program. And those memory sections at least have something or some part of your memory that store your program code, which goes from a certain part. The initialization routines or the reset vector routines plus the IQ routines are at a special part of the memory that is mapped at the start that you need to know when doing this. You commonly have something called an interrupt and output map. This is the connection between the sensors and the actuators to the outside world or to external pins on your CPU. And all the rest of your main memory, if you look at a very basic machine model of for C, is two things. You have a so-called dynamic memory and a static memory. And the difference is when this memory is allocated. And allocation means that you reserve a certain part of memory for modification later in your program. You can either do this while your program is running and have this dynamically and reuse it, or reuse memory for different parts of your program, or you can have it statically allocated, which means you reserve it before you execute your program during compilation time. And C, per default, only supports two things, and that's complete global memory, static memory, that's basically allocated during compile time. There's something also called a heap, which is kind of dynamic, but not directly in the C standard. So we'll just ignore it for now. We just say, okay, there's static memory. This is something we allocate while we are compiling our program, while we are writing our program. We say, okay, there's this one integer that my program will require during the whole lifetime of while it's executing. And then there's a different memory, the so-called stack memory. And this stack memory, this is allocated during the execution of our program and allows us to reuse certain parts of our memory. So usually memory is scarce. That's why you want to do as much recycling or reusing as possible. And this stack, as we will later see once we come to function, this actually follows the so-called scope, again, something that we'll look at later, of our function. So if you have your C program, let me give you a small example. You have, for example, a function that does something like this and something like this. Execute something, modifies those, which we define here. Then we have another function, our main function, or we can have a main function, which could then be the entry point to our program, which then executes. And what you see here, that's a C program. If you compile this with a compiler, it will translate this stuff that I've written here into an assembly language, so into a stream of instructions that can jump around and that you can execute and then load into the memory address. So this will be translated to assembler, loaded into a program memory. And then once we reset our CPU, the initialization routines actually initialize the hardware and then start to execute this program instruction by instruction by instruction. And what I've done here is to allocate memory. And this allocation are those two things. I've defined 4 variables. So whenever you have memory inside of a program, you call it a variable. This basically means you have some kind of memory that you want to modify. In this case, I defined 4 integers, A, B, C, and D. Both of the type integer. That's what we have written here. And the only difference is that I've written a static keyword before one allocation, and for the other I haven't. The difference is now where this is placed and how long those variables live. The thing is, if I execute this fn function at some point, then my instruction sequence basically means, okay, I jump there. And what then happens is that during this lifetime, while the program is inside of those curly braces, so inside of here, while it is here, there will be A, B, and C allocated on the stack dynamically, right? So while I'm inside of those curly braces, I can modify this part of the memory, do whatever I want with it. While the static keyword is exactly what it says. It means allocate this variable on the static memory. So this will be here in the static memory and will be allocated throughout the lifetime of our program. Now, once at some point everything has to end, so we also end our function at some point. We leave this block with a return statement of something. And once we leave this block, these 3 variables that we have allocated on the stack will get deallocated. This basically just means we free the memory again for reusing from something else. This follows exactly the scope of our function. So those variables only carry a value as long as we are inside of this function where they have been allocated. While this other one, this static one, if we now enter this function again, we reallocate A, B, and C, maybe on a different part of the stack, depending on where we caught it from. But the value of D is still there. This has been allocated statically. This is a global, well, not necessarily global, but a variable that's in static memory. So this will be allocated throughout the lifetime of the program. And that's basically how we handle variables in C. So you either you give it a name for this variable, so an identifier. It usually has a scope on how long it is valid, right? So this follows either the curly braces signature inside of our function block, which is this one here. That's our function block. It has a type. This basically means how many bits are required to store it. What kind of value does it have? We'll look at this in a second. And whether it is allocated dynamically, which means it lives only a part time of our program execution, or if it's static, which means it's allocated in static memory and globally available. Okay, so we had those those two questions, I think, but I would suggest we take a small break of 4 minutes and continue on with more C and how to allocate variables at 5 minutes after 9. Cool. Let's continue on. So, as I said before, with VHDL, the basic thing that you need to do for every programming language is your classical hello world. That basically means generating some kind of output with a toolchain that you have for whatever programming language you want to do. So let's do this for C. I have prepared something, which is kind of stupid to prepare this because basically it's very simple. In this case, this is the most basic C program that you can have. There are a few assumptions on this one that makes it not pure C, and that's basically the availability of this printf function. That depends on what kind of platform you're running on. This is usually if you have some kind of POSIX platform or like a properly implemented C environment, then you have this printf function. It's not always available. For example, if you program the Arduino platform, you don't directly have this printf function, but you use something else. But nevertheless, this is what we are starting off with. Okay, so I think it's large enough to that you can see it. So we need to do this, and this printf function, this basically comes from a module called stdio, shorthand for standard input-output, that you have on your platform, whatever it is. The main basic thing about C is to include those different memories, which then basically tells C++ or tells C or the program that you're writing that there are different functions and variables available to you. That's what those include things do. So you include different modules, and then you define your own functions that you want to have. And now for C, there's always one entry point into your program. Again, this differs from platform to platform. The de facto standard for C is this main function. This basically means if you, again, have a properly implemented environment, you have this main function available. If not, then they might be called differently. This is something that you need to figure out for whatever platform you're programming. But for now, we can assume this main function to be available. This main function usually has a return value, and that's what we are defining here. So if you type something like integer main with this normal braces, then with curly braces behind it, what this means or what this tells our C compiler is that there will be a function that we call main. So it will generate a so-called symbol with the name main, which has no arguments if you call this function. So this is just like a part of the program that you use that you can give certain values to. In this case, if we leave those braces empty, it means there's no argument to those. It will return, however, an integer value. Execute this program. And now, once we have defined this and told our compiler about the availability of this, we have the curly braces. These define our function. This defines our function body. This is the instructions or the sequences that we program into, or that we tell our program should be executed one by one. So this is similar to the execution cycle that we have seen before. We have statements in our program, and you can see those statements. These are things that end with this semicolon. We think before a semicolon is a statement in one line, and these will be executed one by one after each other. In this case, for this Hello World program, we define our main function, our main entry point into this program, and then we say the statement, okay, please call another function called printf. You told the C compiler beforehand that this printf function is declared in this stdio header. Give one argument to this printf function. That's what's in these braces in the gene. That's a string constant, hello world. And once this has been executed, this is one statement, should be executed. Then we return from this function, we return a 0, and this is what our program does. Okay, so now if we click on run, this online GDB, this is quite nice because we don't have to install any tools. So usually you would now have to install some kind of C compiler on your platform, store this in some kind of file, give it to the C compiler, have an executable that is coming out of this and execute it, all handled by this platform at once. So what we see here is the output of this program will be hello world. Well, not super trailblazing, of course, but the thing about this is that usually this printf function is connected to some kind of output on whatever machine you're running on. In this case, we run it on some external server, and this external server output, or the program that is executed on this external server, the output of this program is then connected to this shell that we have here. All right, so that's the first thing that we can do. Now, this thing is called online GDB. Anybody knows what GDB stands for? Yeah. Yes, that's the GNU debugger. And the GNU debugger that allows us to actually stop our program at some point in memory. And that's, I start with this because usually if you stop here and not introduce a debugger, you usually just have some kind of weird idea about what is happening. But this debugger actually allows you to inspect exactly this machine model that I've told you before. So if we now push here and see this small red button that arrives here, this means that we have set a so-called breakpoint. And this breakpoint means once your program arrives at this line in your program, it stops the execution and drops you onto a shell where you can then interact with the debugger, so to say. So let's execute this. Let's debug this program now. What you see, the view changes a little bit. We don't directly have an output here, but we are actually dropped to some kind of interactive shell, which says GDB, so the GNU debugger, where we can type something in. And to the right-hand side, you see different kind of information about your program. So one is the call stack, the other one are local variables, then there's an expression display, and the breakpoints and watch points. Now the breakpoint, this is one of the red buttons that we already have, that we have set. We stop our execution there. That's where we are actually currently at. No, not yet. There are the local variables. These are the things that we define inside of a function scope, which are either statically or dynamically allocated, and we can look at the values here. And we have a so-called call stack that's basically gives us a stack trace. This stack actually is a view of which function we are currently executing. So if we call another function, for example, printf function, then we enter this function, and the call stack actually is the main routine that we have that's on the bottom of the stack, and on top of this one we put we put our printf function. In between those printf functions on the stack, we put our local variables. That's where we allocate them, so that if we return from a function, the only thing that we have to do to deallocate those variables, this memory again, is to reduce our stack by a certain amount of variables, exactly the amount of variables that we have allocated before entering this. That's the idea behind this. Then the display expressions is basically where we can do something with whatever C we have. Now this debugger, as I said, allows you to look into the machine model, so you can look at the current values of your registers that you have on your PC. Or you can inspect the current memory that you have at any point in time. So you can usually break the program at different points in time. So what we first have to do is to run this program, then it executes it. Then we see, okay, now we stopped. Or what we see here is once we stop, then once we run the program, it stops at breakpoint 1, which is here at line 15 in the main program. We haven't seen anything, but we can basically do it. Can do something called a backtrace. This backtrace gives you an idea of your call stack, or basically returns your call stack of your program. You can also see it here. We are currently, call stack is not very deep. We only have a single level. This is basically inside of the main function. And we already executed the printf function, which basically then we can inspect the memory and so forth if we like. There's not much to look at the moment. So we just continue with the program. And we see, okay, now there's the output of our printf, and that's basically it. Now let's say we want to look into a little bit more detail what the printf function actually does. For some reason we are interested in that, whatever that might be. What we do is to set a breakpoint now at a line higher. Before we execute the printf function, we run the program again because it stopped, and now we stopped at the printf function. Now we can either continue, this means we jump over whatever this function is until it returns and then continue on in this one, or we do a single step, and that's we call step. What we then have, or what you see here, is now we stopped, we executed a few instructions until we entered the printf function. That's what you see here now in this debugger. So we stop now at the first statement of our printf function if it has debugging symbols. In this case, your compiler tells, or the debugger tells you, okay, we don't have the source files for the printf function, so I can't tell you what kind of statement is currently executed. But we see that the call stack is modified, and that we have different variables here. For example, the argument value that we have as a local variable here. Right, so here we can't do much. We can call the next statement, but since we don't have the debugger here, we could basically look at the assembler that is running on it, but that's basically it. We can step through this function now until we hit the return statement and move up to the call stack again. Right. So we can execute it to, so if we do run again, it starts again. But if we continue, it basically executes the program until the end again. And that's basically it. So with this debugger, what you can do is to stop the program execution at any point in time and start to inspect this machine model that we have looked at. Right. Now what is happening here in the background when we push debug or run is that this program or this part of the text that I've written here is going to be compiled. Compilation means that you translate from this textual description to a list of instructions. And then this list of instructions that's expressed in assembler. This is then, there's still, and this is basically what you can execute already, but there are still references to all the symbols that are included there. And those symbols are other functions that are going to be called, for example, this printf function that is declared, and global or variables that need to be mapped into the main memory. So this compilation step, so usually you say, okay, you compile a program, and what you mean with it is that you do a compilation, assembly, and the linking of the whole program. What this means is, but what it actually means is that you do a compilation. This means you translate this textual C description to an instruction of assemblers with symbols included. And then you do a linking step, and this linking step does nothing more than resolve these symbols. So if you have a reference to the printf function, then at some point you require or you need the actual compilation or the instruction sequences needs to know where exactly in the memory the code for this printf function is to be found. And this is what your linking step does. This linking step looks into symbols and what kind of symbols are defined, and then either tells you, okay, I can't find the source code to that, or it's defined in a so-called library. This might either be a static library or dynamic library, or it's somewhere mapped into the memory already, and resolves those symbols then from a textual description to an actual address inside of your main memory where this can be found. That's the idea behind this linking step. Right. So that's the hello world from one view, from this so-called debugger view. The other view that you can take is this one. This is again a similar tool to the online GDB. The difference here is that that it actually allows you to inspect the compilation result. So compilation in the sense that the step from a textual description to the actual assembly code, not the linked assembly code, but the compiled code. So now if you go here and do the hello world again, so So in this case, we have to do integer main, and but this one, we define a function body. So again, it's a main function that returns an integer eventually, and this main function should print out something. In this case, I wanted to print hello world again. I stop, or I basically tell, okay, this is the statement that I want to do for the compiler. This is what should be executed at one point. And once this statement has been executed, that's basically all I want. Now, let's see. Does this compile? Actually, it shouldn't. So this is, so what you see here in this pane, it's called pane, is actually what the compiler tells us, whether it gives warnings or errors, and as you see, it gives quite a few warnings. One is that you can't find, or that it's an implicit declaration of the built-in function printf. What it means is actually that the compiler needs to reduce kind of the declaration of this printf function, which it tries to. It actually says, okay, there's a printf function with a string argument, which is not existing in this case. So what we have to do, and that's good that the compiler tells us, is to include the file that actually declares this function. In this case, it's the std.aio, which is here. So I include that. The compiler is silenced. Perfect. Okay. So cool. What you see here is it's colored actually. So what you see on the left-hand side is the C program that we have. On the right-hand side, on the middle pane, that's actually the actual assembly code that is generated for that program that we execute. Now we compiled it for x86 for an x86 assembly instruction set. We can of course also compile this for ARM, either with a Slang compiler or with the GNU compiler. Let's go for the latest ARM GCC, and then we see, okay, this changes. There are different assembler instructions or opcodes, mnemonics that actually execute it. But if you compare it in a little bit more detail, you see that there are similar things or similar concepts that will be translated here. And one thing that you see here, which is common to the x86 version and the ARM version, is this first instruction here. So if you have a function definition that we have here, it gets translated to those two instructions. Okay, so again, this is something that I'd like you to ask for somebody who has a little bit of experience in assembly or can guess what is happening here, why those two instructions are here generated at the start of the function. Sorry? Yeah, this is for the stack pointer, exactly. So can you explain what exactly is happening here, or what the stack pointer is for? Yeah. So it's a parameter storage, for example, yeah, and we keep track of where we want to return to. That's what we push on the stack. So the stack is, as the word, or you can imagine this as the word it says. So we basically have a stack start, and we just put things on top of this stack. And what you do at the start of a function is actually to push the return function for this function. So if we later on execute a different function and at some point hit the return statement, we retrieve this the address of where we were called from. So if you call a function, we push the return address to the stack. Then we usually also put the arguments and parameters for our functions onto the stack, on top, on top, on top, on top. And we know that this difference between calling a function and actual, or the parameters and the return address is constant, this offset. Right? So if you have, I don't know, 4 arguments for your functions, you always increase it by 4 plus the return address 5. And that's what's happening at the header of this, at the start of this function. You basically increase the stack to this thing. So this isn't done by the caller, but actually by the callee. And this is what's happening here, the stack pointer modification. This is a simplification, of course. Not everything that not always the return address will be put on the stack, and not all the parameters will be put on the stack. For ARM, for example, you have special registers that actually store it for a single level push, for single level calls, for example, to optimize this. So there it's stored in a special register sometimes. Right, but this is what the stack is for. So this is the first thing. You allocate the memory that you require for your parameters and for your local variables as well by increasing the stack pointer. And then based on the top of the stack pointer, you can go backwards to actually have the allocation for your variables. You can see this by, if you actually now say, okay, I want to have a local variable in here. If the optimization is turned off, which can do like this, optimization, then you see that the stack pointer should have changed. This. And yeah, you see, I think this one is then the stack pointer modification to allocate a variable for E2. Right, anyway, there's the printf then that's going to be executed. So here you see two instructions, and then finally, which I think is the address for the string constant that's going to be pushed here into this register. You can see this by this LC0, which refers to this label on the top here, which defines the string constant that we have here, that we move into register 0, and then we call the printf function with a branch and link instruction. So it basically just calls the printf function, and that's what you see here, what this assembly still is. This is a symbolic reference to the printf code to be executed, which we haven't resolved yet. Right, so this is still missing. We don't know at this point in time where the printf function body is stored inside of our program memory, which is then resolved in the linking step. So in the linking step, then we either copy the code into the program memory, or we know that it's to be found somewhere. Right. Then once this function returns, we remove our stuff from the stack again, and finally return from this function. Now here we do an implicit return. If you do something like this, this can lead to a bug because we actually declare the function to return something, but it doesn't. So what's still missing here is this final return statement, which is then pushed onto the stack. But here you see that what you do in C is this kind of is you define everything or most of the things into a function. This function has a return value, it has a parameter. It can define local variables that are either allocated on the stack or on the static memory, which is if we add a static in front of this definition of A2 here, then will not be allocated on the stack anymore. So the stack pointer won't be increased, but this will be somewhere in the static memory, allocated in the static memory. Which means that that it will keep its value in between runs of this function. Otherwise, it will be resetted all the time. And then we have a list of statements to be executed by our compiler. And the first statement is to allocate the memory and initialize it with a 2. First statement is then closed with a semicolon. Then we have the next statement, which is called a printf function with the argument hello world. Statement saved. Once this has been returned, the next statement is to return from this main function and be done with this function. You can see that what we actually do with C then is this compilation, where we go from this textual description of what should happen into multiple instructions on our whatever CPU that we have. And once we start our CPU, it starts exactly at this main entry point and starts to execute this instruction. That's the first clock cycle. Then it starts with the next instruction, executes this one. Then the next clock cycle executes this instruction, and so forth. And what it modifies, or what those instructions are, arithmetic, branching instructions, and comparison functions. And that's mostly all there is. Everything else is just a complication on those 3 types. What we modify is those registers, usually. and we store and load those registers back into the main memory. That's what's happening all the time on our on those machines and the machines that we program. Right. Cool. So that was our hello world function. So we basically go from that one, and you can try at home. So these are online tools that actually hide all the complexity between calling the your compiler and defining a C program. You can try this at home as well, of course, or on your own machine. Anyway, the basic thing about C now is, and that's true for most imperative languages. Imperative in this sense means that you have one instruction that needs to be executed, and the next instruction, and then the next instruction. And instructions is expressed in kind of different ways for all those imperative languages. In C, we have two things, and these are sequences of statements that are actually executed. You can get more details about all the statements. It's actually quite short here on this one, but you basically have a statement is what is executed at one particular time on your CPU. That's what C does. Everything between a semicolon is actually one statement. And those statements that can be there are made of expressions. Those expressions are then can be arithmetic expressions, it can be comparisons and so forth. And those expressions can be then compiled to multiple instructions, and those instructions and statements are put into sequence, what we've seen in the Godbolt tool. So what you do is to have different expressions. So for example, this one here, to include something, which is basically just copy the content of this file, that whatever I have in between here, the standard IO file, just copy this into this current file, copy it together, and then have this as an input. You can do declarations of variables and functions. In this case, I define an integer or the main function, which returns an integer, and now it has two arguments. And its function body. And the function body, that's actually the so-called, if you want to go deep into this definition of statement and expression, it's a so-called compound statement. So you can put together multiple things, but then in the end, you have statement 1, statement 2, and statement 3, which is then executed one after the other. That's what we do here. Okay. Now this gives you like an intuition of how to do this programming in C. Now we need to understand programming in C. We need to look at 4 things, and that's what's there to come. The first one is to allocate and type memory. That's basically done with variables and the type system in C. The next thing is to have the control flow, basically how to control the execution. So these are, if you know programming already, you know those constructs. It's if, while, for loops, and so forth. So comparison and loops. That's what we look at. Then the next thing will be structuring of instructions. We had a small taste of this already with the functions and how to do this in C. And it's basically also how to include modules, but it's mostly handled by the include by this include macro. And then the last thing is, and that's a little bit, I hope I have a good explanation for this one, pointers. So sometimes this is a construct that is a little bit hard to wrap your head around, but this is actually the thing to that actually makes C so efficient. And that's also something that, if you know this construct, you know what's happening behind all the stuff in your high-level programming languages, and why some executions are sometimes super slow, and sometimes you can make them a lot faster. And that's by use of pointers, which is basically a different way, or it's just a way of addressing memory, so to say, and modifying this. All right, these are the 4 things that we are going to look at next. So let's start with the simple stuff with types, and I'm doing a similar basically just a definition of what is available. So the C type system is not strongly typed in this sense, but depending on the definition, it is. But what you have is those basic types. You have a void type, which basically means it has no type. It's empty. It's undefined, whatever type it is. So you need to convert it to a different type once you want to use it or interpret it. Then there's a character type, which is 8-bit, which gives you a character and also a value, so to say, for printable characters. There's a short, which is 16 bits, integer 32 bits, and so forth, long, and 182 bits. And there's float and double for floats and double precision floats. I've written here usually between all of those things. And this usually means that it is not defined by the C standard how wide those types should be per default. So you can have a platform where your character is actually 16 bits wide and not 8-bit wide. It's not a good idea, but it is possible, and it has been done. You can have platforms where your short is actually 32 bits wide or only 8-bit wide. Again, not a very good idea, but has been done and can be done. There are compilers that actually do this. So that's why this usually is there. So for most of the time, you can assume this, but it's not guaranteed. That's why if you do programming, or if you want to do programming and you want to make sure that your variable has a certain precision based on a bit width, you use something called a std int header. That's a standard int header. And there you have then types like integer, the amount of bits that you like, and then you do an _.t as a suffix, just to make sure that that you refer to this type. Right, so that's what you want to use for most of the programming, this uint and integer type T instead of using the defaults that are defined there. You can then have different modifiers, signed or unsigned. So this should be clear what is used here. For the signed type, you can also use the standard int type. You just remove the u in front of it, but if you have the u in front of it, you refer to the unsigned integer type. That's most of the stuff for integers. Floats and doubles are usually a little bit less tricky. They are standard defined. They are always 32 bits or 64 bits. Most of the time. But there are almost no platforms that have shorter or longer things there. And the other thing that you need to check out is, since you are so close to the machine, the endianness of your types is not per default defined, but this depends on the actual platform that you compile for. Who of you knows why this is a problem, or where you can see this problem, or what this endianness refers to? Exactly, yeah, it's right, but not. It's yeah. I also can't remember which one is which. Usually, because it's not a very good mnemonic. It doesn't refer to the bits though. It refers to the bytes. So an 8-bit type doesn't have any endianness. You always interpret it the same way. The most significant bit is at the left-hand side, the top one, and the least significant bit at the lower-hand side. This is different for big endian and little endian machines. So here you actually have the choice. You can either have the most significant bits at the top and read it from left to right, or the other way around. Actually, you can also do it like this, where the least significant byte is on the left-hand side and the most significant byte is on the right-hand side. The difference between those, one is little endian and the other one is big endian. Okay, so the chat actually says big endian is the most significant bit on the lowest address. Yeah, so if you have lowest address on the left hand and so forth, you can imagine that one. Now, it is, as I said, it refers to the bytes, not to the bits. There's no, so this endianness, this refers to whether the most significant byte or the least significant byte is on the left-hand side. Any idea why this is a problem, or why you wouldn't want to look into this? Exactly. So, so your answer is, if you transfer it somewhere on the bus line or on any bus line, then it matters how it's interpreted. That's absolutely correct. So if you have, so it doesn't become a problem if you're on a single CPU and just calculate with it. And of course, it doesn't matter whether it's little or big endian. But once you transfer an integer to any other component in your system, it starts to matter, because there it might be interpreted differently. And the common thing is, for an embedded system, is that you have your CPU, as you refer to a bus line, and you have some kind of sensor And then you transfer data between this one. And your CPU now might interpret all these things as little endian, while your sensor interprets all the stuff in big endian. So now if you transfer the data byte by byte, for example, 16-bit integer of the ADC result, and you interpret it, then just have this byte array and interpret it. Interpreting in C is called casting. Cast it to an integer of 16 bits. And those bytes are basically the wrong way around for the interpretation. You have stored it big endian, so you might, for example, say, okay, the least significant byte is on the left-hand side, but your CPU actually interprets it the other way around. You get a weird result, right? So you get a super large value if it should be when the sensor actually sends a small value. That's why this matters, and that's why you need to think about it. So whenever you transfer data from any component to any other component, between CPUs, between machines, you need to make sure that you know about the endianness of your local CPU and whatever the source of your values are. Exactly. So the chat has the same thing. So for C, if you want to do this, there are a few functions to help you in exchanging those bytes. So the only thing that you can do about this is if you want to reinterpret it, you of course exchange the bytes or reorient it. And the functions for that in C are called N to HS and N to HL and H to NL and H to NS. The bad thing about C programmers is that they like short mnemonics instead of reinterpreting this. So basically, this stuff is short for network to host short and network to host long. And this refers to the endianness problem. Is usually quite apparent if you do network programming, because you have different systems. One is big endian, little endian. You send integers, you need to reinterpret it. And this big endian and little endian is also sometimes referred to as the network byte order and the host byte order, depending on what you have. And that's why those functions are there. So here you can basically just drop this function in between if you receive. I think the network byte order is big endian and the host byte order is little endian. So this function will only rearrange the bytes if you're on a little endian machine. If you compile this program for a big endian machine, it will just do nothing. Right, so endianness is an important thing. So one last thing about this endianness, we have big and little endian. Sometimes, in very rare cases, and you can probably completely forget about this in a second again, there's also middle endianness. And this middle endianness is even weirder. I can't really remember how it is, but the ordering is not like from left hand to the right hand, but the middle one are also exchanged. It's very, very rare and very weird, but it is possible. Anyway, for you can just remember there's big and little endian, and that's it. Okay. Right, so these are the basic types. So you have this integer types of different lengths, so to say, and also the standard int types. And this big and little endian things, these are basically implicit. You need to know this about programming. There's no way of saying, okay, this type is a big endian integer and this type is a little endian integer. It's basically just an integer where you need to assume which kind of big endians are. Now, this is quite nice to have these basic types, but you usually want to have a little bit more structure about your memory. So you want to, for example, say, okay, this is a kind of an object, and this it's not only an integer, but it's like a collection of integers, like 4 of them, which mean different things, or 3 of them to designate a point, for example, in 3-dimensional space. And what you use in C for that is so-called structs. You group together different of those basic types and align them in memory, so to say. What you can do then is to define a struct. That's the keyword that you put in front of it. It should be actually thick. So this is a struct, this is the keyword, and then you give this a name. In this case, if I want to define this my 3-dimensional point in space expressed as integer variables, then I say, okay, there's a struct called point, and I open up a curly braces and say what it contains. In this case, I say, okay, it contains integers, which I call x, y, and z. What your compiler does out of this is to, if you, and this is just a declaration, so you just say, okay, there's this construct of a point, which I call struct, and you can later on allocate types of this. We ignore the other one at the moment. So this one here, this will be the allocation then. So if I mention this in a program, I tell the compiler to actually allocate 3 integers that are somewhere in memory, usually quite almost next to each other, but not completely. This is a little bit tricky on how they are allocated. But usually you then have those 3 integers allocated with one statement instead of doing the same statement again. You can then access those single values here with this dot operator. So you say, okay, I have this construct P, I have which is of type struct point, and if I want to access one of those things inside of this struct, and I basically do a dot point X, Y, or Z, which you then can read on this one. So this is the struct. So what happens, as I said, usually it's a little bit more delicate than how I'm telling you this, is that you get the struct point, which basically allocates this one here, and you can refer to those three integers then with P if it's going to be allocated. Then there's another one of those compound things. So sometimes you don't only want to say, okay, this is struct which contains 3 integers, but you actually want to say, okay, there is something that contains some kind of memory, and I can either interpret this as an integer, I can interpret it as an integer, as a character, as a 16-bit integers, and so forth. And that's what the union is for. So with a union, you say, okay, here's a block of memory, and it has different interpretations. And how you do this is to use the keyword union to define a new type. So if you allocate this one here, it allocates actually the amount of memory of the largest member of this union. In this case, it's this unsigned integer with 16 bytes. So we have byte 1 and byte 2 here. And we now say with this union, okay, we can either refer to this, in this case, we have allocated directly. We can either go for my variable .a and add 1 to it, for example. This means you interpret this union as an 8-bit value. So it basically means it just modifies the first byte here, if you refer to it. But then later on, you can say, okay, now I have modified the upper half or the lower half, depending on the endiness of your machine, of this byte, and can actually then set it to whatever I want as a 16-bit integer. Any idea, or do you have an idea of why you would want to do something like this? To have a memory block that you can interpret as, so to say, with different types of different values. Yeah, you don't have to allocate separate memory locations. If you want to reuse this kind of memory that you allocated for different things, that's one way to do it. Yeah. With this one, you could implement a endiness check. Would be one way. So what you do then is to basically assign a 16-bit value where you only set the upper half of the 16 bits that should be there, so the most significant ones, and then you can check out what A contains in this case, because this refers to whatever is on the left-hand side of this interpretation. If it then is 0, you know that it's this one endiness. If all the values are set, it has this value that you have set. That would be one thing. A more common use case is, well, this is one use case. A more common use case is basically if you have a binary, so to say, interpretation, if you transfer something from it and the actual interpretation of this one. So let's say we get a sensor value from one of the sensors that I mentioned last time. So from this Bosch sensor, right? So we have what we can do is to read out the registers of this file. If you remember, there was a 16-bit value for the temperature reading, for example. And now what you can do is to and we have to look at the into other types first. What you can do is to define a union of this sensor value, where you say, okay, the first interpretation of this value is no, let's do it correctly. The first interpretation of our value is in binary or as a buffer. And this buffer is of an array type, so we can have multiples of those with an unspecified length behind it. This is one interpretation as a character, and then the next interpretation would be as a 16-bit integer, which gives us the temperature as the sensor value. And now now the type system allows me to actually say, okay, please transfer via I2C or whatever bus a buffer, a char array from the sensor. So what you can have is then to say, okay, this union, which contains these things, I can either interpret as a char array. So I have as an argument this myvar.buff, so this memory block, but interpreted as a buffer of single bytes that should be written to from the sensor, which are transferred then. Then later on in my program, once this has been transferred, I can refer to this as with the actual temperature and interpret this as a 16-bit integer. And this allows me to do different interpretations of the same memory block, but in a way that I can tell my compiler about it. The alternative would be to do a cast. That's basically an explicit conversion. But here I define a type where I'm explicitly telling all other programmers that read my code later on that I use this in two ways of interpreting this. This is the use case for the union. They have different interpretations. Right now, if you can always redefine your types as we had in VHDL. That's what the type def is for. You have seen it here. So instead of then later on, you can type def a struct where you leave out the name here, but you put it in at the back here. And instead of then having to refer to it later on, always with a struct keyword, so struct point p, you can then say there's a point p that I've defined. So that saves a little bit of typing. Yeah. Yes and no. So it's a good question. So the question is whether buffer is just an address, and of course it's, well, if you know about pointers, it's just an address. That's the thing. But this will be we will look into this later on. But of course, what you interpret here is this buffer is the pointer to the memory location where the 16-bit value is stored actually. Right? So that's what you want to have. And once you interpret it as a temperature, you read, you look at this memory address that is there and interpret those 2 bytes that are there. But the inner mechanisms of this is, of course, that the buffer would just be the address to the first byte. What? In this case, the buffer, yeah. This is like the open edge eraser, so to say. This is a shorthand for things. For a pointer. So it's a little bit of an oversimplification here, of course. So what you would need to do to have this is to dereference it, of course, because you don't get directly the address. I'm not sure if this is actually valid, but you could also have it as a pointer here, or just a character actually, and then dereference it for this one. But we will look into this into those details later on when we get to the chapter on pointers. But yeah. All right, so structs, unions, type defs, that's the other one. Then you can have an array. That's basically a collection or a large collection of values that you put somewhere into main memory. In contrast to most other languages, in C you don't store the size of this array at runtime. So this is something that you have to do explicitly as a programmer. For C, you can only say, okay, I allocate a certain amount of memory, and you as a programmer need to care to make sure that your program knows about the size. This is also one of the cause of the major security problems with C. We'll look into this in a second. But what you can do is then basically allocate memory with a static size. So here in this case, we allocate 32 integers, and with this special syntax, we initialize all values to 0. In this case, we can also have multi-dimensional arrays that then depend on how they are laid out in memory. So whether it's the first axis first that will be put right next to each other, or the second axis, and so forth. But it is possible. And this array construct is also used in C to actually handle strings. And those strings are special. Since we don't store the size in C, we need a special trick in C to actually make sure that the size is known. And this is when you have something like this here. You tell the compiler that you want a character array allocated in memory, which the compiler should figure out the size of. In this case, the size of this array that is going to be allocated is 5. For those who don't know C, it could be a little bit surprising. For everybody else, knows that the last byte of this string array will be 0. And it is 0 that you can basically start going from the first character and then move out to all the characters, and to actually figure out the size of this string, you search for this terminating null byte, so to say, to actually figure this out. This is the way strings are stored in C, so basically terminated with a null byte. There's another way of doing this. This is so-called Pascal string. There's different ways, which is actually also quite clever. So instead of basically having this null terminating bit, you prepend, so you basically have 32 bits or whatever size that you can support for your strings, and put the amount of put the length in front of the of this string character bytes. So if you have the length stored here, so in this case it would be 4, then this is called this is a so-called Pascal string. It's called Pascal because Pascal is also a programming language. But anyway, for us, we just remember any string is just an array of characters, and the size is defined by the terminating null byte. So if you don't have this null byte, then most of your string functions go bad, which is, as I said, the cause of some of the major security flaws in C. I'll have an example in a second. So these are arrays. Last things before we see also the pointer type, which is a special kind of type, are enums. And those enums are just string constants that you define. In this case, you define an enum, which, sorry about the layout, you define this enumeration, which you define some symbols. In this case, 1, 2, defined by 4, 3 as the enum. And those values will then get chosen automatically if you don't, by the compiler, if you don't assign them. If you do assign them, well, they will be whatever you decide to choose. They are pretty nice to implement state machines. Now the question here is, what is the value of 1? 0, exactly. What is the value of 2? Yeah, exactly. What is the value of 3? No, it's 5. It actually, that's actually the thing. The enumeration really just goes from the last value and just adds 1 if it's not specified. For fun, I don't know what happens if you assign 4 to 3 as well in this case. I'm not sure if the compiler will give you a warning or if it just will be ignored and you can now refer to 4 with 2 and 3 or not. But the idea is to define those values as a way to, instead of as, so to say, a symbol for enumeration instead of going for doing this explicitly with integers. Right. So as I said, a string type, it's just an array with a null termination at the end. And it's also the first thing where you use this kind of pointer. Size is stored by this trailing null pipe. And as I said, it's a common security problem. It is one of the pointer types. All of those things that we've seen, but the enum type, the structs, the union, the basic types can also be a pointer type. What you do if you want to have a pointer type is to add a star behind it. And the star, so pointer is basically an interpretation in the literal way, like an arrow, so to say, which points to somewhere. So what you do instead of storing an actual value is to store the address in memory of this value. So if you have this character pointer here, as we've defined it here, with the star at the end. This basically means whatever is the value of this variable. So if I define an A here, a character pointing to A, then it means there A actually doesn't contain a character, but it contains the memory address where a character is to be found. That's the idea. So here is something like 0 blah blah blah, and if you then interpret this, memory address, then you know, okay, there's a string that I can hopefully find there. And this star is basically, if you the idea behind the star, why this is star, is that if you look at an arrow from behind, you see this kind of things that you will see, those fan outs. That's the idea behind this. But as I said, we look into pointers into more detail. For right now, try to remember that a pointer is not the actual value, but is actually an indirection, so to say, or the address of where your of the value that is to be interpreted. So fun question, if I define this character A, and if I define another pointer B, how much memory is going to be allocated by those two variables? Yeah, exactly. It's the same for both pointers. That's correct, because they are pointers. So you basically store memory addresses. But do you have an, yeah. Oh ja, ich bin gleich so weit. Eine Frage noch. Do you have an idea of what the size of those pointers is? Yeah. Exactly. So if it's a 32-bit machine, it's 32 bits. Exactly. Very good. Thank you. All right. That's it. Next time, buffer overflows and more on C. See you.